Uncomputable things. These are sort of things or problems which cannot be computed by any Turing machine, which basically means they can't be computed by any real-world computer. Even a quantum computer cannot compute uncomputable things. These include things like, given M and X, where M is a Turing machine, decide whether or not M halts on X. All right, that's the standard example of an uncomputable problem. This is called the halting problem. We talked at length about this last time, or last week. The halting problem. There are stupid jokes about the halting problem, like, I have a halting problem that runs in my family. I don't even know how to say it. It's so stupid. I refuse to say it correctly. But it's like you start saying something about the halting problem, and then you just like stop talking in the middle of a word because you have a problem halting, something like that. It's stupid. This is called the halting problem, to decide whether or not a Turing machine halts on on some specific input. This is a problem which cannot be solved by any algorithm. Is another way you can say it. You can never make, this is why you can never make an infinite loop detector to build into a compiler, even though that would be a very useful thing. It's not possible to do. All right, so that's called the halting problem. Another undecidable thing that we talked about last time was, given M and X, just decide whether or not M accepts X. This is also an undecidable problem. Accepts X, right? That's an uncomputable thing, or to decide whether or not a given Turing machine accepts some X. These you can write as languages. This one we call LH. That will be the language of Turing machines, followed by a string where the machine halts on X. This one we called LU, U for the universal machine, because the best you can do if you want to know if a Turing machine accepts a string is you can run a simulation of that machine and see if it accepts or not. That's called a universal machine, which simulates another Turing machine. The problem with that strategy is that if the machine M has an infinite loop in it, then your simulation will also enter an infinite loop, and so your simulation will not be able to tell for sure, yes or no, if something is accepted or not. All right, I hope you talk to your friends, talk to your moms about this over the weekend, that there are some things that are uncomputable. Your friends and moms might have responded, these are all kind of obscure questions that, one thing that's a little unsatisfying about these questions is that they are themselves questions about other Turing machines, which is a little weird. I imagine if I was talking to this with my mom, she might say, you're just talking about other Turing machines. Are there any real questions that are uncomputable, that are not just questions about computation in the first place? The answer is yes, and that's what I want to talk about today. These are uncomputable things which have to do with other Turing machines. There's also sort of in that category is this number, omega, the halting probability. This is an uncomputable number, which is interesting, probability. This is a real number whose digits are not computable. That's interesting to me, but again, it's sort of another question about other Turing machines. So I want to talk today about uncomputable things which, on their surface at least, have nothing to do with the theory of computation, but they are not questions about other kinds of Turing machines, but they're still uncomputable. So here is a historical example that I won't be able to explain a lot about, but I want to talk about sort of more ordinary uncomputable problems. Uncomputable. This one is something that people have suspected was uncomputable for a long time, but it wasn't demonstrated until the 1970s, so we're not going to do the proof because it's super complicated. I've never tried to read the full proof of this, but this is called the Diophantine equations problem. Diophantine equations. And this is a problem just straight up from ordinary number theory. It's about polynomials, and it's something that anybody can understand. But the question is about multivariable polynomials. For example, something like 3x squared plus 4y minus 8xy. You're allowed to mix the variables together if you want, but it's got to be a polynomial. No square roots or any weird stuff like that. Equals, I don't know, 5x plus 1. And the question is to find the solutions of the polynomial. That is, find specific values for x and y so that when you plug them in, it all is equal, right? Can we solve the polynomial? Now, to just find solutions to a polynomial, I don't know how well you remember your sort of multivariable calculus or ordinary single variable calculus. You can solve a polynomial like this using things like Newton's method, or your calculator has equation solvers in it that can handle this kind of a thing. So can we solve it in real numbers? The answer is yes, you can. Or maybe your real number solver will say there is no solution. But the hard question is, can we solve it in integers? Or say no solutions in integers exist. This is much harder. Those like Newton's method or other kinds of numerical tricks for solving equations, they work on real numbers very nicely, but they do not work if I only care about integers. So this particular polynomial here, I don't know if it has, I just made it up, so I don't know if it has any solutions using whole numbers for x and y, all right? This was a major problem that was recognized as important for a very long, like Diophantine. This is named after the Greek mathematician Diophantus, who was interested in polynomials and integer solutions. So this has been around for a very, very long time. But anyway, in 1970, this was proved to be uncomputable. This question, which on its surface has nothing to do with Turing machines at all, this is proved to be uncomputable. That is to say, no Turing machine can compute the answer to this question. That is, there is no algorithm, no computer program for which you can give it a polynomial like that and ask, are there integer solutions? That is not possible to do with a Turing machine. This is kind of, to me, very interesting. What it means to me as a real life sort of working mathematician, it means that if there's some kind of problem that I'm trying to solve, that, like I do math research and I write papers where I, solve problems that have not been solved before. This is what mathematicians do. What it means is, in real life, when you're trying to solve a problem, sometimes the answer is there is no way to solve this problem. Like that, this is not usually the answer like on one of your homework problems. Like if you're doing math homework, you pretty much take for granted that there is an answer or there is some method for solving this problem. But actually, in real world mathematics, there are problems which have no methods by which they can be solved. And this is an example of one where on the surface, certainly this guy, Diophantus, never thought that this was an unsolvable problem. He just thought he didn't know how to solve it. And that's the usual attitude that mathematicians have. When I encounter something that I don't know how to do, I still more or less assume that I or somebody could figure it out. But actually that's not true. There are some problems that are straight up uncomputable. And the way, can I just say in vague terms, how this was proved to be uncomputable? This was shown to be equivalent to the halting problem. And this is typically how it's done. That somebody figured out a very complicated way to translate. It turns out there's a way to translate a multivariable polynomial into a Turing machine. And conversely, there's a way to translate a Turing machine into a multivariable polynomial. in such a way that solving the polynomial is equivalent to telling if the Turing machine halts or not. And because that's possible, that means that since there can be no solution to the halting problem, that means there can be no solution to this Diophantine equations problem. That's how it's typically done. You show that your problem is equivalent to the halting problem. Now, this one is very complicated, and like I said, I don't want to try and get into the details, but I wanted to show you an example of a real-life, sort of ordinary-looking math problem that no computer can solve this. So like in real life, if you find yourself confronted with a specific polynomial like this that you want to solve, it may be that that particular one can be solved, but there is no general purpose algorithm that can solve any polynomial like that. All right, great. I have one more example that I do want to talk about in general, in detail, I mean, of an uncomputable thing. And this is something you can tell your friends about also. This is called, this has a person's name. Post is a person's name. It's called the post-correspondence problem. The post-correspondence problem. This was created by this guy, Post. I don't know much about Post. He's one of the early sort of second generation of mathematical computer scientists. He was working in the 40s when he sort of came up with this thing, which we're about to talk about. Post is like the next generation after Turing. The people who created everything from scratch were around the like 1910, 20 kind of time period, and then Post was sort of the next generation. Anyway, Post. The only other thing I know about Post is that Post is the first person to use the word string in computer science for strings, what we now call strings. So thank you, Emil Post. Anyway, here's the post-correspondence problem. I'm going to write PCP for post-correspondence problem. This was invented by Post as an interesting example of an uncomputable problem, which on its surface, it doesn't seem weird at all, and it seems like something that you could perhaps find a solution for. It turns out you can't. Here's the idea. If you are given blocks, this is like a little puzzle. Given blocks like this, you have a bunch of sort of tiles. I'm going to draw 4 of them. And each of these tiles has a string on the top and a string on the bottom. And I'm going to write this specific example here. A string across the top and a string across the bottom. 1 and a 0, 1. All right, these are the blocks. This is the setup for a post-correspondence problem. You have these tiles or blocks, and one of them is the starting tile, which I will put this sort of fancy border around. This is the starting tile. All right, and the question is, it is your job to solve the puzzle, is to put those blocks in a certain ordering. So can we arrange the blocks, starting with the starting tile? I suppose I could have written the starting one first, but whatever. Can we arrange them with repeats allowed? Starting with the start tile. So that the goal is you want to put them in some ordering so that when you read, you're going to like line them up next to each other. And what you want is when you read the string all the way across the top, it is equal to the string all the way across the bottom. So it's, starting with the starting tile so that the string read across the top of everything equals the string across the bottom. That's the goal. All right, so in this example, what that would look like is, all right, I have to start with the starting tile. Let's see if we can solve this little puzzle. I have to start with that one. Now I want to arrange the other ones, and you are allowed to repeat them, so I could reuse the first one if I want to. in such a way that the string, when you read it all the way across the top, should equal the string when you read it all the way across the bottom. All right? Anyone have an idea what I should choose next? I'll tell you, here's a little hint. Here's what you should not choose next. Let's not use this one next. Why not? Because the one on the top says 1, 0, 1, 0, 1. Now, across the bottom it says 1, 0. If I want it to be a solution, what I put over here should be like that. Like it needs to read across the bottom, needs to read the same as across the top. Now, I'm not saying it has to be that exactly, but anyway, it definitely shouldn't be this one, right? Because then the thing across the bottom would say 1, 0, 0, 0, 0, which is not going to match across the top. So anyway, what should I use? I saw somebody had an idea. Yeah?
1, 0,
I just gave it away. You should use the first one. Although that, like, we're not really done at that point, but yeah, let's use that one. That's the second tile. Are we done? We are not done, because now if you read across the top, it says 1, 0, 1, 0, 1, 0. Across the bottom it says 1, 0, 1, 0, 1. Any suggestions about what we should do next? Yeah? Yeah, how about the last one? The 1 up top and the 0, 1 on the bottom. All right. This actually is my final answer. So now this thing, when you read it across, it says 1, 0, 1, 0, 1, 0, 1. And when you read on the bottom, it says 1, 0, 1, 0, 1, 0, 1. Yeah. I can imagine making a cute little phone game or something where you have the tiles all lined up and you drag them with your finger to line them up at the bottom. All right. I am here to tell you, folks, this puzzle is uncomputable. There is no computer algorithm that can produce the solution to this puzzle. Now, can anyone maybe shake puzzled at this statement because we just did it? Does that mean we're like some kind of God-level computing here? I am not saying that it's impossible to do what we just did, because we did do what we just did. Anybody feel like you understand the difference? When I say there can be no algorithm to solve this problem in general, what's the difference? Or how did we just do it, if that's really true? Yeah?
This is like a pretty simple example. So if you have a bunch of tiles, it wouldn't really be able to compute it.
Yeah, so all we did was demonstrate that we solved this particular example. And maybe this was an easy one, right? What I'm saying when I say it's uncomputable is I'm saying there can be no computer program which will be able to solve any example you give it. All right? This is a solution, but the whole point of this is that the PCP is uncomputable by a Turing machine. Maybe if you give it a specific example, maybe for that particular example, it will be able to figure it out. But there is no algorithm that can find answers to any possible PCP that you give it. All right, so the PCP is uncomputable by a Turing machine. Does this mean actually you could not make a phone game out of this? No, it doesn't mean that. It just means, like, I can make the puzzles and ask somebody to try to solve them. It means it's going to be really hard for a person to solve them. And maybe, I might, it basically means, like, yeah, you could make an app which presents this puzzle to people. You could not make another app which then solves the puzzle every time. That's not possible to do, but you can certainly, this is another one of those cases where it is easy to check the answer. You can definitely make an algorithm that reads the solution and tells you if it's right or not. The problem is you cannot make an algorithm which just produces the solution out of nowhere. All right? Now, this is simple enough that I want to actually show, so this is our goal for the next, I guess we got 30 minutes here. We're going to show that that the PCP is equivalent to this language which I called LU. That is the language of all strings that look like M followed by X, where M accepts X. All right? We're going to show that solving the PCP is the same as being able to tell if some Turing machine accepts a particular string. So the idea here is we can encode any Turing machine as a set of tiles PCP tiles. And if you somehow had a magical thing that could solve the PCP, then that thing could be used to figure out if any Turing machine halts on a or accepts a particular string. All right. What this means is, I talked last time about sort of imaginary machines with a magical halting oracle or something like that. It means actually if you had a machine with a PCP oracle, then that would be good enough to solve the halting problem and all sorts of other kinds of problems. All right, we can encode a Turing machine as a set of the PCP tiles. And I want to show exactly how we can do that. So let's just do this. I don't want to describe in general, but I want to do a specific example of this. Here is a Turing machine. I'm going to give names to everything because I'm going to want to say very specific things about it. But this is a example Turing machine, which I'm going to try to describe how to turn this into a set of tiles. Or I was going to tell a story. This is a personal story. This is when I was a younger man. Shortly after I started working on research problems, I found a paper. Somebody emailed me, said that you might find this interesting. I was working on something called the doubly twisted conjugacy problem in groups, and somebody sent me a paper where they showed. So I was, trying to find different methods to solve this doubly twisted conjugacy problem. Somebody sent me a paper which showed that in some cases this doubly twisted conjugacy problem is equivalent to the post-correspondence problem, which I had never heard of at that point. And I was like, oh, all right, fine, it's equivalent to something else. But then I looked into it and I learned that the post-correspondence problem is uncomputable. It means the thing that I was trying to do actually was uncomputable. And at that point, it's like, all right, forget about this. Like, you might as well, waste your time on something else. Like, this is something. Sometimes what happens if you show something is somehow equivalent to the PCP, it means you should change careers or something like that. It's not computable by algorithms. Anyway, the idea here is this is a specific Turing machine. I'm going to show you how, if somehow you had a PCP solver, that could be sort of retrofitted into a solver for this Turing machine that would tell you whether things are accepted or not. All right? And let's say we have this Turing machine. This is my machine M. And then with the input string x equals, let's say, AB. And I want to know, is AB accepted? That's the big question. Now, of course, this is a small enough example that you can easily just tell by looking, by running a simulation of this machine in your head. Is it accepted or not? And actually, it is accepted in this case. You will notice something a little weird about this Turing machine is right here. I have an accepting state with more arrows. That ordinarily, we would never do that on our Turing machines because as soon as the machine enters an accepting state, it stops and it's over. So this arrow, with the traditional interpretation, this arrow never happens. But this, what I'm trying to indicate here, just for simplicity with the PCP thing, ordinarily I will not do this, but this is a Turing machine. I will say the Turing machine clears the tape when it accepts. This is always easy to do if you want to sort of rework your Turing machine slightly so that after it accepts the string, it blanks out everything in the tape. That's what that little loop thing does. It turns all A's and B's on the tape to blanks. That ends up being convenient for the PCP thing. Anyway, is x equals AB, is that actually accepted? So let's just work it out ourselves. Is x equal AB accepted? What do you say? So I'm going to write down an old-fashioned kind of derivation here. I hope you remember how to write these. In state 1, I see an A. I do this arrow. A stays like it is. Move to the right and go to state 2. So this now becomes A to B, right? Next, I have in state 2, I see B is this guy, so I stay in state 2, keep it as a B, and move to the right. This is now A, B2, right? Maybe I'll write a blank there. I usually write a blank if it's on the end. And then I have, actually I'm not going to write a blank. This is slightly important with the PCP thing. And then I'm going to be in state 2. I see a blank. I go to the left. So it becomes A3B, right? That's because I was here. I forgot my little arrow. I was here in state 2. It says BBL, so I go back to the left. So I end up in between the A and the B, and now I'm in state 3. And now this is accepted, but it's going to do this loop a couple times to clear out the tape. So the result of this will be blank the B and then move to the left, and then blank this A and move to the left, and I end up with just sort of a 3 there. All right. So because of this blanking the tape, accepting means you just end up with a 3 by itself at the end. All right. Okay. Check it out. So this is Post's big idea, and this is really very clever in my opinion. We can translate this entire scenario, this diagram here, and this derivation here. All of this we're going to translate into blocks for a PCP problem. So this, and I will tell you the way that it goes. So translate this into PCP tiles. In this example, it's not so complicated. And really, I mean, following this example, you can do this for any Turing machine. So first of all, there's sort of tiles in a few different categories. There's basic tiles for the letters, and they just look like this. And you have to use these every so often. And then there's a tile that looks like this. So the idea is the tiles here, we're going to, you stack these tiles next to each other in certain ways. We're going to stack them together so that they end up making derivations like this. And so my goal is to tie together these tiles in various orderings so that they make legal derivations on the Turing machine. So basic letters are like that. And then we also have tiles which represent moves to the right. Move to the right. These tiles look like, okay, I will write down one of them. Unfortunately, I have to scroll back up. 1A up top and A2 on the bottom. So what this represents is, if I'm in state 1 and looking at an A, what happens? Well, if you look on the diagram, if we're in state 1 and you're looking at an A, this happens. That says it stays as an A, you move to the right, and you change to state 2. That means this little fragment of what you were looking at, it used to be state 1 looking at an A. Now it looks like the old A is on the left now, and now you're in state 2. So this, you could think of this as representing one little arrow in the diagram. And then each of the arrows in the diagram, we translate into tiles in this way. So that was one of them. There's a slight difference in the ones which move to the right versus the left. That's why there's going to be 2 categories here. Anyway, the next arrow to the right, this BBR on here, that means if the 1 is looking at a B, it looks like this. And what should look like afterwards, the B should stay like it is, and the 1 should move to the right. The next one is the looped edge on the 2. BBR on 2 looks like 2B, B2. Because you stay in state 2, but you move to the right, and the B stays like it is. And then there's one more R arrow here. This one, AAR, going back from 2 to 1. So that, when I make a tile out of it, it looks like 2A, A1. All right, those are 4 tiles corresponding to movements to the right. And then we have the movements to the left. They look a little bit different, as you know, and as we've said before. Moving to the left in these derivations is mysteriously more complicated a little bit. So the moves to the left, I will write the first one. This one is easy, A2, 2A. Is this easy? If you're in state 2, that represents this block, BBL from 2. So if you have 2 with a blank on the right, you can move back to the left, and it will still be A. And the other, this also says sorry, that, I'm confusing myself. I'm not sure that's correct. I have it written on my paper. I'm trying to convince myself that it's right, but I think maybe that should be a 3. A2, 3A, I think. This says if you're in state 2 on the right side of an A, you can do this, this arrow changes to state 3 and you move to the left here. And then the other one would be B2, 3B. These two together represent this arrow here, BBL. Sorry to be scrolling so frequently. All right. All of those L arrows, basically they come in a few different forms, because when you're moving to the left, it depends on what used to be on the right also. But I'm just going to write these down, and if you like, you can take my word for it. There's one that just looks like that. That's also the BBL. If you have 2 with a blank on one side, you can just move to the left, and it turns into a 3 with a blank. There's also ones. Yeah, these 3 sort of all go together. This is the move to the left when the 2 is looking at a blank. If there was an A on the left, it moves to the left past the A. If there was a B on the left, it moves to the left past the B. And if there was nothing, it moves past nothing. All right, and then if I have a left arrow, I just have to write these 2 guys. These are the last 2 arrows. This one, A blank L, really turns into several alternatives. If you had something like that, then it becomes that. This would be if I'm in state 3 looking at an A, I should blank this and then move to the left, and it should look like 3A. And similarly, what if it looked like B3A? Then it should look like 3B. And what if it looked like just 3A with a blank on the far side? Then it should look like just 3. And then I have similar ones with B's. I'm going to try to squeeze them in here. We're almost done here. I want to just work out the example derivation here. B3B and 3B. And finally, 3B and 3. All right, these are the movements to the left. They kind of fall in 3 categories. Those are the 3 different arrows. Each of them has to turn into several tiles. This is a bit ugly. All right. We have 2 more tiles, one representing the starting state and one representing the accepting state. So the accepting state, and these are a little weird. These look weird. They have to look this way just so that everything works. The accepting state looks like this. 3 with the arrow, and then on the bottom is a epsilon, an empty string. Of course, these strings can be the empty string. They're just not in any of the other ones. And then the starting state, and this is required to be the starting tile, looks like empty string across the top and then 1 AB arrow. That's the starting tile. All right. See if I can put these all on the screen at once. It was specifically 1 AB arrow on the bottom. That's because my intention is to lay these tiles next to each other to create this derivation, right? And that's why I started with 1 AB arrow on the end. And the last part of the derivation is arrow 3, which is why this, well, actually, when we make the derivation work out, it's going to end up with an extra arrow at the end. That's just a technicality because of the way to get rid of the extra arrow is a real pain. But that's how this is going to work out. All right. Can we show, I want to show directly how writing this derivation is equivalent to solving this PCP problem. So if I start with this, I hope you have these. I'm going to try not to scroll too far here. Maybe I can fit it all in here. So here is my, let's try to solve the PCP. Or maybe I should say solving the PCP. PCP is the same as a successful derivation. That's the point of all of this, right? And because, like I said, deciding if successful derivations on the Turing machine exist is uncomputable. That means solving the PCP must also be uncomputable. That's the point of this. But can we demonstrate how solving the PCP is the same as a successful derivation? So to solve the PCP, I must begin with this starting state, epsilon, and then one AB arrow, all right? And now what should come next? Now, we have the advantage of already knowing the answer. The derivation, which is at the top of the screen, that's the string that I expect to end up with across the top and across the bottom. So I want to say 1AB arrow followed by the next part of the string I already know should say A2B, right? Anyone want to suggest which tile I can use to make that happen? Across the bottom, at least, I want the next part of the string to say A2B. Yeah.
First move, right?
Yeah, the first move to the right, this one here. This is the only way you can make a A2. So this, I use A2. Well, it's just that one tile, which will make, I suppose, a small portion of what I want, right? A2. Now, sorry, I'm off the bottom. Now, actually, I want it to say A2B across the bottom. I can make that happen by just using this letter tile, BB. So I'm going to put that one in too, BB. And because I'm following a legal Turing machine derivation, you can see sort of magically, when I read across the bottom here, the top is matching so far, right? The top says empty string, which doesn't matter, and then 1AB, which actually is the beginning of the derivation down here. All right. Anyone want to suggest what should I see next? Yeah? The arrows, yeah. Because I'm trying to end up with this derivation, right? I'm up to this point, at least on the bottom, A2B. Next, I want to see the arrow. Hopefully, I also want the arrow on top, and actually, I do also want the arrow on top. It all works out kind of magically. So this is arrow, arrow is the next tile I'm using. All right. What comes next? I'm at A2B on the bottom. Next, I want to see AB2. Can I make that happen? Yeah?
You first do the two, just the AA.
Yeah, first do A's and A's. All right.
Is it the third move to the right tile?
Yeah, and then this tile here, moving to the right, 2B, B2. So I go 2B, B2. Great. Now on the bottom it says AB2, which I wanted. And you should just verify for yourself. The top is still saying what I want it to say. 1AB arrow A2B, which is what this says. 1AB arrow A2B. What should I put next? Yep. The arrows, yeah. That's sort of one more step that I just did. And now I want the arrows again to do my next derivation step. On the bottom it said AB2. What I want it to say now, I'm looking here, after AB2 comes A3B. That looks like one of the moves to the left. Now the A here is basically unchanged from where it was before. So I think I want an AA block. And then I want one of the moves to the left, which gives me a 3B. I think it's this one, B2 and 3B. Yeah, I think I like that one. B2 and 3B, like so. I think I'm still looking good as far as you have to make sure that as you read across the bottom, it's always the same as you read across the top, or the same so far at least. And I think I'm feeling good about this. All right, next is the arrow, because that was another step. Next is the arrow. Next is the A3B. I want it to look like just 3A. So you want to look for a tile which maybe, I think that's this one, right? This one actually makes A3B and 3A. So I go that one next, A3B and 3A, like so. All right, another arrow. That's my next step. I'm going to have to go down to the next line, sorry. My scrolling situation is getting even worse. Now I have 3a down here. I want it in the last part of this, I want it to end up with just 3. That, I believe, is this tile right here. 3a on the top and just 3 on the bottom. So this is now 3a and 3. And basically we're done at this point with the derivation, but we need to make the top sort of catch up with the bottom. As you look at this, you'll notice basically what we have is the bottom is reading a derivation which is always one step ahead of the top. And so we need to allow the top to also finish. So I'm going to do one more of the arrow, and then finally what I called the accepting state tile. Gives me 3 arrow on the top and epsilon on the bottom. And that's the end. If you read now, the whole thing across the top is equal to the whole thing across the bottom. All right? So in this way, if you had some kind of magical PCP solver that could always find these solutions, then automatically you would also be able to tell if a Turing machine accepted any input. That means, since we already know that's not possible, that means the PCP is not possible to solve. All right? So no, my big conclusion here is, maybe I'll write this. Any PCP solver could be used as an oracle for, really we were talking about that language LU, that is a particular string accepted or not by a Turing machine. Any PCP solver could be used as an oracle for LU, and since LU is undecidable, that means automatically that PCP also must be undecidable. It's not computable. There can be no such oracle with a Turing machine. All right. The end. And actually, any thoughts about that or questions about that? I find this very interesting, that there are more or less ordinary looking problems which are actually not solvable by any algorithm. There can be no algorithm to solve this problem. All right. You might ask, like, are there any real world problems that are not solved by any algorithm? I would say, I don't know. I can make tiles like that in the real world and give you a stack of them. You know, that's a real world problem. I don't know if it's very important in the real world, but yeah, I'm not aware of real important, you know, technological problems. Like maybe, you know, people are trying to make like self-driving cars. Maybe that's just impossible. I don't think so, but I mean, humans could drive cars, so probably computers can too. That's my own opinion, though. All right, that's that. And actually, this is the end of everything that I wanted to do for the semester. We have 2 more class meetings left. I had intended to use one of them as like a, you know, review for the test, as I have done in the past. But I don't think we need to use the other. Is it obvious? It's not obvious to me. Is it better if we cancel class tomorrow and come on Friday, or should we come tomorrow but cancel class on Friday? That's the question.
Oh man.
I'm far removed from your position in life, so I wasn't sure how to answer this question. I don't care either way.
We don't have another quiz.
Yeah, that's true.
Yes, there will not be a quiz this week, so the quiz is irrelevant.
Will we get the review sheet tomorrow then, or Friday?
Well, yeah, so whenever we have class, I will hand out like a practice test like I have in the past. That will either be tomorrow or Friday.
Cancel tomorrow.
Tomorrow's earlier in the morning, so maybe that matters. All right, so let's meet on Friday and not tomorrow then.